Section 3.1 Inverse Functions. To get started, let's revisit the concept of what we mean by a function. A function f between two sets A and B is a rule or a mapping which assigns to every element in A a unique element in B. Using mathematical notations, this means that x1 if x1 and x2 are the same in the set A, the domain, it follows that their images must be the same in B, meaning f of x1 and f of x2 must be also the same in the target set B. This begs the following question. Does the converse of the statement above hold? In other words, if f of x1 and f of x2 are the same, do we necessarily have that x1 and x2 must be the same? So in other words, do we always have the right to left implication, this red implication on the screen? If the images, if f of x1 and f of x2 happen to be the same, do we necessarily have that x1 and x2 must be the same for any function f? The answer is no. To see this, consider, for example, the squaring function, the function that squares the input. And think about this function. What's f of 1? F of 1 is equal to 1 squared, which is also 1. And what's f of negative 1? F of negative 1 is negative 1 squared, which is also 1. So these are the same. So we have that f of 1 is equal to f of negative 1, which means we've satisfied this condition. So the images are the same, yet 1 and negative 1, these guys, so these inputs are not the same. So yet 1 and negative 1 are not the same. So we have that this this happens to hold, but this doesn't, this holding doesn't force this to hold, because f of 1 and f of negative 1 match, yet the inputs 1 and negative 1 are not the same. So the converse of this doesn't hold all the time. So I'm gonna just put a big X on it. In general, this is not true. Now, for those functions for which this implication happens to hold, they're gonna be referred to as one-to-one functions, and this is the next definition that we're about to mention. Okay, so the next definition is, again, it's about the converse. So the converse, any function verifying the right to left implication, is gonna be called a one-to-one function. Okay, let's read it. So a function f is called a one-to-one function if whenever the images are the same, it follows that the inputs are the same. If you want to put it in words, this means that no element in the range is the image of more than one element coming from the domain. Equivalently, this implication also means the failure of this has to force the failure of this. That is to say, if x1 and x2 are not the same, the two images must not be the same as well. And if you want to verbalize it, this means no two distinct elements of the domain of the function have the same image. Let's take an example. Let's go to the book and go to page 364. Let's say number 8. Look at number 8. The question is, identify if this is a one-to-one function. I'm talking about number 8 right there. So remember, the x coordinates are the inputs, the y coordinates are the outputs. And for the function to be one-to-one, it means no y coordinate, no element in the range, so no y coordinate is the image of more than one element in the domain, which means no y coordinate is shared by multiple inputs. So let's see. This y coordinate 1 is the output if the input is negative 14. And I see nowhere else the output 1. So 1 is not shared by multiple inputs. Negative 14 is the only input that outputs 1. And you can run the same thing, the same analysis for all the other outputs, 3, 4, and negative 2. 3 is not shared by any other input except negative 2, 4 as well, and negative 2. So there exists no y coordinate that's shared by multiple x coordinates. As such, the rule or the relation given in number 8 is a one-to-one function. Let's go to number 11. Look at number 11 right here. So 2 is the output if you input 13. So for 2, so far so good. 3, if you plug in 25, you get 3. So 3 is not shared by multiple inputs. 4 is not shared by multiple inputs as well. However, this relation here is not a function to begin with. If it were to be a function, it would have been a one-to-one. But remember, based on our definition here, a function is called a one-to-one function. So the relation has to be a function to begin with. And that thing here is not a function because 25 doesn't have a unique output. So it has double outputs, 3 and 4. So this is not a function to begin with, let alone being a one-to-one. 12. Look at this. 13 doesn't have multiple pre-images. It doesn't have multiple x's. So far so good. However, 25 does have multiple inputs that produce 25 as an output. So there exists an element in the range, which is 25, that's shared by multiple or by more than one input, which is 3. And hence, I'm violating this thing here. So there exists an element which is the image of more than one element in the domain. Okay. Pictorially, how does it look? Take a look at number 17. Do you see any y coordinate that's shared by multiple inputs, by multiple x coordinates? I see a lot of them. For example, this y coordinate 2 is shared by multiple inputs, namely negative 1 and 1. If you plug in 1 or negative 1, the output is 2. So there are two distinct elements of the domain of the function which have the same image. As such, the function is not going to be one-to-one. So this is not one-to-one because there exists an output which is shared by multiple input, or because there are multiple inputs, there are distinct inputs that share the same output. For example, output 0 is shared by probably this is like negative 3 over 2 and 3 over 2. Okay, so what type of characteristic can we say that kind of like go hand in hand with the vertical line test for functions? It's about a horizontal line test now. If you can find a horizontal line test that passes more than once, through the function, through the graph of the function, then this function is not one-to-one. And this is what we have as a next property. It's the horizontal line test, and it goes like this. A function is one-to-one if and only if no horizontal line intersects the graph of the function more than once. With this in mind, let's do one or two more examples. How about 14? The function is a discrete function here, is just points. Is this a one-to-one function? Certainly this is a function because it passes the vertical line test. There exists no vertical line that passes through the function more than once. And how about horizontal line test? The horizontal line y equals -3 passes through the function more than once. As such, this is not going to be a one-to-one function because input 0, input 1, and input 4 have, all of them have that image -3. So this is not a one-to-one function. It is a function, but it's not one-to-one. How about 20, let's say 22. Well, 22, even though it passes the horizontal line test, but it doesn't pass the vertical line test, which means it's not a function to begin with. And to be a one-to-one function, it has to be a function. So this is not even a function, and hence it cannot be a one-to-one function. Moving on, let's define what we mean by an inverse function. So let's suppose the following context. So we have a function f that's defined on A with values in B, and let's say that let's suppose that this is a one-to-one function. A function g that goes backwards from B back to A. So f goes from A and outputs things in B, and g now goes backwards from B to A. We call that g is an inverse of f, provided the following two conditions hold. And these conditions read as follows. If you compose f with g in any order, so if you compose f with g from the left or from the right, you plug in an x, the output remains that input x. In other words, f and g, they undo each other, they neutralize the effect of one another. So it's like a neutral machine. Once you compose them together, you plug in x, you get it back, and this happens no matter how you compose the two. Both of them should hold. Remember, composition of function is not commutative, meaning if you compose f with g in this order, there's no reason to believe that it's going to produce the same thing as if you compose them in the reverse order. So composition is not commutative. The order matters, as you can recall from our discussion when we defined the composition of functions. So as a concrete example, if the function f adds to the input a certain amount and g subtracts that same amount, I'm expecting that, the two functions are undoing each other's effect, which means I'm anticipating them to be inverses of one another, and hence they're gonna verify the two conditions labeled as 1 and 2 here. Let's take an example. Let's suppose that f is the function f of x equals x plus 5, so it adds 5 to the input, and g of x is the function that subtracts 5 from its input. And the question is, are f and g inverses of one another? As we said, we're expecting them to be inverses, and let's verify it. In other words, I want to verify conditions 1 and 2. I want to show that 1 holds and 2 holds. So let's start. So for condition 1, I want to look at f composed with g and I want to input x, and the idea is I want to get x at the end of the day. All right, let's see. Well, f composed with g at x, by definition, this is f acting at g of x. And this means f acts on the output of g if the input is x, which means on x minus 5. So what's going to sit here is x minus 5. And let's look at how f operates. Well, f adds 5 to its input. Whatever the input is, f adds 5 to it. So the input in this context is x minus 5. So f of that entity is going to be this entity plus, right? The input, the entity plus 5. So plus 5. And this is obviously x. So condition 1 is verified. We get that this guy is equal to this guy. So if you plug in x in the composite function f composed with g, you get back the x. So as long as you are composing them in this order, there's no action. You plug in x, you get it back. So condition 1 is verified. Are we done? No, because if 1 is verified, that doesn't force that 2 is also correct. Remember, composition is not commutative. This may happen, but this may not. So I need to check it by hand. So let's do it. For 2, I need to compose them now in this order. G composed with f, and I'm gonna plug in x. And this is the same as g acting at f of x. And in this context, f of x is x plus 5. So this is gonna be g acting at x plus 5. And what does g do? Well, g of anything is the thing minus 5, and my thing here is x plus 5. So it's going to be that thing minus 5. And this is immediate, this is x. So what do we get? We get that if you compose the two in this order, now you plug in x, you get it back. So condition number 2 is verified. So condition number 2 is verified. As well, right? Okay. Long story short, both conditions are verified, 1 and 2. And if functions f and g verify both of these, they are inverses of one another. So we infer that, as expected, this f and this g are inverses of one another. So I'm gonna just say here, yes, since this discussion holds. All right, so let's now go to the book, and let's take one of these examples. How about 32? So we have h of x is 7x minus 3, and k of x is x plus 3 over 7. And the question is, determine if the two functions are inverses of one another. So let's go here. So the question again, this is on page 365, number 32. So I have h of x, as we said, is equal to 7x minus 3, and a k of x is equal to x plus 3 over 7. And the question is to determine if they are inverses of one another. Again, to be inverses, it means I need to verify if these two conditions hold. So if you compose them in any direction, you plug in x, you get it back. Well, let's compose them in this order this time. H composed with K act first, and then that action is followed by the action of H. Well, this is the same as H of K of X, which means X plus 3 over 7. Let me write K of X. So H of K of X, which is H of X plus 3 over 7. And how H operates, it multiplies the input by 7 and subtracts 3 from the result. So the function H is going to multiply the input by 7, and the input is x plus 3 over 7, and then it's going to subtract 3 from the result. And this is the same as, we can simplify by 7 here, and we get x plus 3 for the first, as the first expression minus 3, which is simply x. As such, we can infer that condition 1 here is verified. We're going to move on to condition 2. Remember, I want both of them to hold. So I'm going to move on now to 2 and verify it. And see if it's going to be verified. K composed with H at X. Oh, this is K acting at H of X, which is K acting at the output of H if the input is X, which is 7x minus 3. And once you take a look at how K operates, this is how K operates. It takes the quotient between the input plus 3 and 7. And the input happens to be 7x minus 3 in this case. So that's going to be the quotient between the input plus 3 and 7. And the input is 7x minus 3. And this is the same as 7x minus 3 plus 3 is 0. So upstairs is only 7x. And then downstairs is 7, and this is simply x. So condition 2 is also verified. So condition 2 is also verified, and hence 1 and 2 are verified, and as such, the two functions h and k are inverses. So h and k are inverses of one another. Okay. Let's take another example. Let's go to 34. So 34 is, you have two functions p and q as such. Let's copy them. So this is 34 now. Okay. So I have p of x equals minus 3 plus x divided by 4, and q of x is equal to 4x minus 3. And same question. It's the same question, are they inverses? So let's compose them. Let's start by composing p with q in this order, and let's plug in an x. If you do plug in an x, you get p of q of x, which means p of q of x is 4x minus 3. And what p does is it adds negative 3 to the input and divide the result by 4. And the input happens to be 4x minus 3 in this case. So that's going to be the quotient between negative 3 added to the input, which is 4x minus 3 and 4. And this is what? This is the quotient minus 3 minus 3, this is minus 6, plus 4x over 4. And as um, you may observe, if you try to compare this with x, I mean, is this the same as x? This is the question. It's not hard to see it. They're not the same. But we have to clarify. So they are not the same. But we have to clarify why. For example, let x to be, I mean, for these two guys to be the same, this entity and this entity to be the same, they should be the same for all x. If they're not the same, it means they differ at least for some x. So they're not the same for some x, at least, for you to be able to say that they're not the same. Let's show it. Let's choose an x where this guy, this quotient becomes not this guy. How about choosing the most economical one, which is 0? Let's take x to be 0. The right-hand side becomes 0, but the left-hand side is simply negative 6 over 4, which is certainly not 0. So this quotient and this guy are not the same. For this x, as such, they're not the same at all. Because if they were to be the same, they should be the same for all chosen x's. What can we say then? P composed with Q acting at x is not x. And as such, condition 1 fails to hold in this case. So condition 1 fails to hold in this case. And as such, P and Q are not inverses. We don't even need to check the second condition, because even if the second condition holds, I need both of them to hold. You see the end? I need both of them to hold. If one fails, we're done. We don't even need to check the other one. Okay. So just change the color here. So we can conclude. So it follows that P and Q are not inverses. Okay. A natural question to ask at this point is, do all functions have inverses? And the answer is no, but there is a class of functions for which the inverses exist. And this class is the one-to-one function class. So the property reads as follows. Every one-to-one function f that goes from its domain to its range has an inverse. The construction of the inverse is not that hard. If you want me to prove it to you, I'll be very happy to do it, but post it on the forum on Canvas, and I'll record a video to this effect. Here's another property. An inverse of a one-to-one function is unique. So the inverse, when it exists, is a unique thing. There are no more than one inverse for a given function, if that inverse exists. Let's actually show this. Let's prove this. So how do we show that the inverse is unique when it exists? Well, I'm gonna suppose I have two inverses, and I'm gonna show that they are the same. So let's suppose there are two inverses and show that they are the same, and then as such, the inverse must be unique. You're gonna tell me, oh, what if there are three inverses? Well, if there are three inverses, I can choose two of them, and since once I show that any two are the same, hence all three have to be the same, and so on for other, if you can imagine other number of functions that behave as the inverse of, or as an inverse of a given function. Okay, so let's see how the proof goes. So proof of this last property. Suppose that f has two inverses. Let's call them h and g. What does it mean? So that is, what does it mean for h to be an inverse of f? Remember, it means that the two conditions 1 and 2 hold. So f composed with h acting at x is x, and h composed with f at x is equal to x. So I'm going to write this down here. So that is f composed with h at x is equal to x, which means f of h of x is equal to x, right? And h composed with f acting at x is equal to x. That is to say, h at f of x is equal to x. And so this is for h to be an inverse of f, and also g is an inverse of f. So g is gonna verify the two conditions as well. So I'm gonna write them down. So and f composed with g at x is equal to x, which means f of g of x is equal to x, and g composed with f acting at x is equal to x. That is to say, g of f of x is equal to x. And what do I want to show? Let's write this, let's write what we want in red. So the goal is to show that the two inverses that we suppose they exist, the f and the h and the g, are the same. So the goal is to show that h is equal to g, right? This is the goal. And when are two functions the same? They are the same provided they output the same thing for the same input. So if you plug in something here, you plug in the same thing here, you are expecting them to be the same. This is when two functions are equal. They produce the same output for the same input. All right, so let's plug in x and an element x here and see that it's going to produce the same thing as if I plug in that x on and g. So h of x is equal to, look, I have all these four at my disposal I can use. I'm gonna look at x. You see the x here? I'm gonna look at this x as f of g of x. So I'm gonna rewrite the x as f of g of x. So I'm gonna keep the h. I'm gonna rewrite the x as f of g of x. Why I can do so? Because I know that x is equal to this thing. So I rewrote it as such. And then this is equal to, this is equal to h composed with f at g of x, correct? If you hide this for a second, this is the same as h composed with f at this thing. Well, how does this operate? This is h of f of that thing. H of f of that thing. It's the same thing, right? It's right there. Very good. So these two things are the same, and I'm gonna use this property that I have here, which is the same as this property. Take a look at this property here. This says if you compose H and F in this order and you plug in whatever you plug in, you get it out, right? So in other words, H and F neutralize each other. Okay, and look at this. H composed with F acting at this. That's the thing that's taken the role of the asterisk. That's the thing. So what do I get back? H composed with F, no action, you get back the asterisk. So the asterisk is in this context g of x. So I'm gonna get it back. And now look what we have. So we have that this guy is equal to this guy. Isn't that what we wanted to show? Very good. So H and G are the same. They produce the same output for the once you plug in the same input. As such, the two functions are the same, and hence, when an inverse exists, must be unique. You cannot have multiple inverses for the same function. So because the inverse of a function is unique, that inverse we can label it because it's one and only one thing. So we can label it and we can give it a name. And this is our notation then. By virtue of the foregoing property, this one, the last one, the uniqueness property of the inverse, the inverse of a function f has a special notation because it's unique again. It's denoted by this figure here, this image. And it's read as the inverse of f, the inverse function of f. This is not f to power negative 1. It looks like f to power negative 1, but it is not. What it is it verifies the two conditions 1 and 2, remember? 1 and 2, these two conditions here. So I'm going to rewrite them, but now instead of having g, I'm going to have the special notation f inverse, because that g is unique and it's labeled as f inverse. So I'm going to have this this notation. I'm going to have the two properties written above as follows. If you compose f and f inverse in any order, they neutralize each other. You plug in x, you get back x. Okay, so let's take an example. Suppose f of 1 is 5, f of 3 is 7, and f of 8 is 10. Find f inverse of 5, f inverse of 10, and f inverse of 7. Remember, f inverse is the inverse function. It's the function that undoes the action of f. Whatever f does, f inverse undoes it. So if f assigns or sends 1 to 5, f inverse is gonna reverse the effect. F inverse of 5 is gonna be 1, correct? Once again, if you plug in 1 in f and you get out 5, f inverse is gonna reverse that that process. If you plug in 5 in the inverse function, you're gonna get back 1. So this guy is simply 1. And similarly for the rest, f of 3 is 7, so f sends 3 to 7, f inverse is gonna send back 7 to 3. So f inverse of 7 is simply 3. And lastly, f inverse of 10 is 8 because f of 8 is equal to 10. So f inverse is gonna reverse that process, and it's gonna give me 8 as an output if I plug in 10 in the inverse function. Okay, here's another example. So find the inverse of the one-to-one function f of x equals 5x minus 2. Well, 5x minus 2 is an oblique line. It's a line that goes, which has a y-intercept at -2. So as such, it passes the horizontal line test. Remember the horizontal line test mentioned earlier, and this is equivalent to the function being one-to-one. And since every one-to-one function has an inverse, this property, every one-to-one function has an inverse, we infer that this function must have an inverse, which is to be determined, and hence the meaningfulness of the question. So how do we get our hands on that inverse? Let me do it in one way. We know that the inverse of a function reverses the effect of that function. So let's study how the function f is operating. Well, this is the process of f. You plug in x in f. What f does, it multiplies that input by 5 and then subtracts 2 from the result. So if you plug in x in f, it's going to multiply it by 5 first. This is, let me just label this. This is multiplication by 5. The small action, the small subfunction here. And then f is going to subtract 2 from that result. So I'm going to get f of x minus 2. So this last thing is subtraction by 2. Right? So the first one was multiplication by 5. The second one is subtraction by 2. And this whole thing is f, right? This whole thing is f. Oops. So this whole thing is f. F inverse is going to go the other way around. So it's going to reverse the effect of each one of these pieces. So if this piece is subtracting by 2, it's going to add 2. So if we start by a number y, I'm constructing f inverse by hand. So if I plug in y in f inverse, it's going to undo this last part, which means it's going to add 2. And I'm going to get y plus 2, right? So it's going to add 2. I'm going to get that input plus 2. And then it's gonna undo this part, which means instead of multiplying by 5, how do I undo multiplication by 5? It's division by 5. So you get division by 5, and then you get y plus 2 over 5. So it looks like that this is the inverse function f inverse. Okay, so if you want to write it, we write f inverse of y is equal to y plus 2 over 5. Now if your favorite letter is for input is x, here I plugged in y. Y is a dummy letter that's representing the input. If your favorite letter for input is x instead of y, you can erase this guy, and this is the same guy here as well. So you can erase it and rewrite it as x. Again, what did I do here? That y that you see here is a dummy letter that's representing the input in the f inverse function. If your preferred letter for input is x, rename that y to be x, and then you get, instead of this y and this y, you're gonna get x and x. All right. Okay. But this is not the best way to construct f inverse. As you can imagine, because what if f is a way more complicated looking function? How can is there an easier way to construct f inverse as instead of just constructing each piece or reversing the effect of each piece of the function f. Is there an easier process to do so? To figure that out, to answer this question, let's try to revisit the definition of f inverse. So we know that if y is equal to f of x, so which means f takes x to y, then this is the same thing as f inverse is going to reverse that effect. So f inverse is going to take back y to x, correct? So if f takes x to y, f inverse is going to take you back from y to x. And this is simply the definition of f inverse, right? All right. So if you look at this from the equation standpoint, this side, this statement means that you have an equation which is solved for y. And what this says, if you are able to solve this equation for x in terms of y, this is an equation solved for x in terms of y, then you got yourself the inverse function. Okay, one more time. If you are able to write, so from the definition of f inverse, we can infer the following. If you are able to transition from an equation which is solved for y in terms of x to an equation which is solved for x to f inverse, which is solved for x in terms of y, then you got your hands on the f inverse function. Let's apply this over here. Let's do it again. So over there we had the function f of x equals 5x minus 2. So we had y equals 5x minus 2. This is what we had over here, right? Now if we are able to solve for x, then we got our hands on the inverse function. Let's try to solve for x here. What would you do first? Well, we add 2, right? So we're solving for x. We're gonna undo this thing. Remember, this is reminiscent to that, right? I mean, we're not doing anything else, but here the process is gonna be smoother because you're used to it from previous courses. Okay, so I'm solving for x. I'm gonna add 2, and then I'm gonna get 5x equals y plus 2. And then in order to solve for x, I want to divide by 5. Again, you are really undoing the action of multiplying by 5. So this is, these two things are the same. So dividing by 5 amounts to writing x equals y plus 2 over 5. And then what this says, if you are able to solve for x, then you got your hands on the inverse function. So this guy here is the inverse function, f inverse of y. That's the definition of the inverse function, f inverse, which is exactly as we found before. And remember what we said? If your preferred choice of input is x, rename y to be x. So instead of this y here and instead of this y here, you're going to write x and x as we found before. Okay, so this is the process. Let's now go to the book. And let's go to one of these examples that we have from 41 to 52. Let's choose a couple. How about we choose number 50? So we have v of x equals x minus 5 divided by x plus 1. And they told us that this function is 1 to 1. We don't have to check it. And the question is, find its inverse, because if it's a 1-to-1 function, it must have an inverse, as you remember from a previous property we discussed earlier. The question is, find that inverse function. Okay, let's do it. So this is again on page, let me just change the color. So this is on page 365, number 50. I don't know what's going on here. Right. the function is Vx equals x minus 5 divided by x plus 1. And the question is to find V inverse. All right. So as said earlier, the process is this is y equals the function. The function's name here is v, okay, and we're gonna try to solve for x. Guaranteed, this is guaranteed to happen. I mean, because the function is 1-to-1, and they told us in the problem. So I'm gonna be able to solve for x. The question is, what do I get on the right side? Whatever I get, that's the v inverse that I want. Okay, so let's start. So y is equal to x minus 5 divided by x plus 1. I'm solving for x. This is the same thing as saying y times x plus 1 equals to x minus 5, which is the same as yx plus y equals to x minus 5. Let's bring all the x's on one side. We get yx minus x is equal to minus y minus 5. Correct? And remember, what am I doing? After x, I need to solve for x. How about we factor x on the right side, left side, and get y minus 1, the quantity as a factor, equals minus y minus 5. And this is the same as x equals negative y minus 5 divided by y minus 1, as long as y is not 1, right? Because if y is 1, then this guy would be 0, and I cannot divide by that. So as long as y is not 1, I get this. And what did we say? Once you do so, that side, that guy, that's the V inverse function that you are looking for. So to finalize that, so you can say that V inverse of y is equal to negative y minus 5 divided by y minus 1. One more time, if you don't like y to be, if you're preferred, I mean, it's customary to write the input as x. If you prefer the input to be written as x, rewrite y to be x, and then you get V inverse of x equals negative x minus 5 divided by x minus 1. Okay, let's do another problem. So we did 50. Let's do one of the last two here. So how about 52? So we have g of x is b times x plus a cubed plus c. The input is x. So b and a and c are given to you. They are not the variable of the function. They are not the variable here. B, a, and c are called parameters. Okay, they are given. Once you choose them, you can talk about g of x. Anyway, so let's find the inverse function here. We don't have to show it's 1-to-1. They told us it's a 1-to-1 function. As such, the inverse is going to exist. And the question is, what is it? Let's go for it. So this is problem 52. Okay. G of x is equal to b times x plus a cubed plus c. Okay, so same process. This is y equals b times x plus a cubed plus c, and I want to solve for x. This is the same thing as y minus c is equal to b times x plus a cubed, which is the same as I'm gonna now divide by b, assuming that b is not 0, obviously. because if b is 0, I cannot divide by this b. So as long as b is not 0, I can divide by the b and get x minus plus a cubed is equal to y minus c divided by b. And then to undo the action of taking the third power, I'm going to apply the third root function to both sides and get x plus a is equal to the third root of the quotient y minus c divided by b, which finally means that x is equal to the third root of y minus c divided by b minus a. And what do we know at this point? We know that this side is the inverse function if you plug in y. So that guy that you see here is simply g inverse of y. Okay. The last concept in this section is to try to answer the following question. How about the graphs of f and f inverse? Are they somehow related? Let's take a closer look at what we have so far. So we know that if a is equal to f of b, that's the same thing as saying that b is equal to f inverse of a, correct? By definition of the inverse function. What does this mean? Well, if a is equal to f of b, remember, every point on the graph of, if you have a function g, every point on the graph of g is going to look like something g of the thing, right? Or the same thing. Correct? Well, if you know that a is equal to f of b, this means that the point b comma a is on the graph of the function f, correct? Because f of b is the second coordinate if the first coordinate is b, and that point belongs to the graph of the function f. But if f of b is a, this means b comma a is on the graph of the function f. So I'm going to write this down. So b comma a is on the graph of f. Right? Okay. Let's keep this thing here. I'm going to use it again. Now for this side, you have b equals f inverse of a. So in this context, the function is f inverse, and the input is a. So a comma f inverse of a is on the graph of f inverse, but f inverse of a is b. So a comma b is going to be on the graph of f inverse. So this is equivalent to saying a comma b is on the graph of f inverse. Right? Okay, so this guy here is equivalent to this guy here. These are the same. but this side is equivalent to this green part, and this side is equivalent to this green part. So what can you say about both of the green writings? They must be equivalent because each one of them is equivalent to something which in turn are equivalent. So these guys better be equivalent to each other then. So this guy here and this guy here are equivalent. They are the same thing, right? Let's read it then. If the point B comma A is on the graph of f, this is the same thing as saying that A comma B. So the coordinates are swapped. A comma B now is on the graph of f inverse. However, there exists one and only one axis on the plane through which you reflect and you swap coordinates. And that axis is the line y equals x. Let me write that. So there exists one and only one axis through which we reflect a point and obtain a point whose coordinates are swapped. Oops. And look, I can show you this, but it's gonna take a long time to show it. If you are interested in the proof why there exists one and only one axis that does this job, and to be more precise, namely y equals x, please write on the forum on Canvas. Just create a forum on Canvas and ask me to record a video to that effect, and I'll be happy to do so. Just in case you're interested. I don't want to record it and bore you if no one is interested. So long story short, the graph of f and the graph of f inverse are symmetric with respect to this line. This is the conclusion. Okay, so let me record this. Conclusion. The graphs of f and f inverse are symmetric with respect to the axis or the line y equals x. Okay, so let's do an example. Oops, I see a typo here. All right, let's take an example from the book. Let's go to page 366 and let's choose one of these problems from 71 to 74. How about 72? Let's take a snapshot here. Okay. Okay, so the question is, again, graph the inverse function. So this function is f. We need to graph f inverse. And we know how to graph f inverse. based on the discussion, the observation we just made before, the graph of f and f inverse are symmetric with respect to the line y equals x. They already took the time to actually graph y equals x for us, this dashed oblique line here. So this is the line y equals x. And we would like to graph the inverse function. So the symmetry of each point through the dashed line, through y equals x, is going to be another point whose coordinates are swapped. Okay, all right. So let's find the symmetry of this point here through the line y equals x. Well, this point has coordinates 0, comma, -3. So let's label this. This is the point 0, comma, -3. And the symmetry of this through the line y equals x, as we said, it's gonna be the point whose coordinates are swapped. So the coordinates are gonna be -3, comma, 0. So we're talking about this point right here. So that's the point. That's the symmetry of this point with respect to the line y equals x. The symmetry of this point through the line y equals x, what's this point? This point is 3, comma, -1. The symmetry of this point through the axis y equals x is the point whose coordinates are -1, comma, 3. So this point right here. Okay. And all these points here, the symmetry of all these points are gonna belong to the line segment joining these two points, because obviously the symmetry of a line through a line is also a line. Since the endpoints were 0, comma, -3 and 3, comma, -1, the new endpoints are going to be -3, comma, 0 and -1, comma, 3. So we get this axis, this line segment, sorry. Okay. All right. And lastly, let's figure out the coordinates of this point. Well, this point has coordinates 5, comma, 2, right? 5, comma, 2. And symmetry through the line y equals x is the point whose coordinates are 2, comma, 5. So that's the symmetry of this point here. Okay. And the symmetry of this line segment is going to be the line segment joining these two bullets. And we get this. So what is this red graph? This is the inverse function of this black graph, which is f of x. So that's going to be the graph of y equals f inverse of x.